Okay, 6.3 exponential functions. So we've talked about linear functions, right? They graph lines. Here we have exponential functions that are going to graph more of a curve thing, and we'll look at that in a minute. So an exponential function is a nonlinear function, right? It's not a line, right? It's a nonlinear function of the form y equals ab to the x, where a cannot be 0 and b cannot be 1. Nope, it also says that b cannot be 0. Oh, excuse me. Nope, it's greater than 0. I'm sorry. As the independent variable x changes by a constant amount, the dependent variable y is multiplied by a constant factor, which means consecutive y values form equivalent ratios. All right, what does that mean? If we're looking down at this table down there, whenever we were looking at lines, we would look and see, well, what do we add each time, right? We would do the little swoop and we'd say, well, we add 1, right? Now we're going to look at what would we multiply by. Okay, what would we multiply by? Just to see what the general equation would look like, let's look at this thing here. So this is y equals ab to the x. We say a is, I don't know, we'll say a is 1 for now. How do I get it to 1? Oh, there we are. We'll say b is more than 1. Well, if it's more than 1, it's going to look like this. Let me see if I can make that. So it looks like that, right? It has that curve. It goes up. If it were to be less than 1, it would do something more like that, right? So if b is between 0 and 1, it'll rise to the left and fall to the right, or actually it would end up hitting that x-axis. And if it's more than 1, it would do the opposite thing. All right, we see how it changes there. That's for b greater than 1 and b less than 1. Now let's look at a. As a gets bigger and smaller, well, if it's negative, it flips it down. If it's positive, it stays up. And the bigger it gets, what we're changing right there is actually the y-intercept there. All right, we can see right there it's at 4 whenever a is at 4. Well, actually it's 4.1. And if we put it down to 2, well, there it is. If we put it down to negative, it touches it at -2 and -4. So whatever a is, that's going to be your y-intercept, and b is going to decide how quickly it grows. So let's look down here. Example 21. Does the table represent a linear or exponential function? So I told you earlier that we're going to be looking at what could we multiply by? Well, from 3 to 6, we'd multiply by 2. From 6 to 12, we multiply by 2. 12 to 24, we multiply by 2. So this is an exponential. It's an exponential function. Example 22. Is this linear or exponential? Well, to get from 0 to 4, we couldn't multiply anything. We'd have to add 4. And then we'd add 4 and another 4. Because we are adding each time, this would be linear. Example 23, evaluate, and this is supposed to say y equals -3 times 6 to the x for x equals 2. So what they're saying is just plug in 2. So if we were to plug in 2, we'd have -3 times 6 squared, which would be -3 times 36, which would be -108. Example 24, this should say y equals 4 times 1/3 to the x for x equals -3. If I were to plug that in, I'd have 4 times 1/3 to the -3. That would be the same thing as 4 times 3 to the third, right? That -3 tells it to flip that fraction. This would be 4 times, I don't know, was that 27? 27, which I believe gives us, again, 108. All right, looking down here. Now I talked about this earlier, but let's talk about it again. We'd have y equals ab to the x, where b is greater than 1. Y equals ab to the x, where 0 is less than b is less than 1. All right, let me show you again this on here. We'll make a nice number like 1. If b is bigger than 1, then it's going to look like this, right? This is looking like this thing over here. Whereas if b is between 0 and 1, it's going to look more like this. That's the purpose of these two graphs. It's to tell us that if b is more than 1, it's going to show exponential growth, and we'll talk more about that. This one over here would be growth, and then over here, this would be decay, where b is bigger than 0, but smaller than 1. Now we also have in the middle here, this paragraph, an asymptote is a line that a graph approaches more and more closely. The x-axis is an asymptote for the graph y equals ab to the x. Now notice that. Let's look at this thing here. If I zoom really far out, that red line is just getting closer and closer to a horizontal. It never would actually touch the x-axis, but it's getting closer and closer to it. So the x-axis is the horizontal asymptote for this graph, right? We see that it starts to hug the axis right here, and forever it's just going to keep getting closer and closer, but never actually touching it, right? That's what an asymptote is. An asymptote is a line that the graph keeps approaching, but never actually touches. All right, example 25, graph and compare to the parent function, identify the y-intercept, asymptotes, and the domain and range. All right, so this is supposed to say f of x equals 9 times 3 to the x. Let me put some space here. I'm going to do a short little t-chart for this. If I plug in a -3, I would get out 1/3. If I plugged in -2, I would get 1. If I plugged in -1, I'd get 3. If I plugged in 0, I'd get 9. And if I plugged in 1, I'd get 27. Right? All I did there is, earlier, I typed those into the calculator so that I'd have them ready. So looking at graphing this. I have -3, 1/3. That'd be somewhere in there. -2, 1. -1, 3. 0, 9. Well, that'd be somewhere 3, 4, 5, 6, 7, 8, 9, somewhere in there. So if I were to draw this curve in, it would look something like that. All right, the y-intercept, that would be 9, right? We get that from the a. What else do we need? The asymptote. The asymptote is going to be the x-axis. Domain. Domain, we still have no domain restrictions, so it's still going to be all reals. And then the range, we have to look at that more. Down here on the left, it's going to keep getting closer and closer to 0. So we're going to have 0 is less than y. And then this arrow is going to go up to infinity. So we'll say less than positive infinity. All right. Let's go ahead and type this in here. That way we know it for certain. We have 9 times 3 to the x. So this is what it would look like. We have a significant dot at 9, right there. There's our y-intercept. And that looks a lot like what my graph there looks like. On homework, I'm happy if you just have the one dot. Whenever it asks to graph it, make sure you have the y-intercept correct and at an actual point. The rest of it you can just kind of sketch in. You can type it in a graphing calculator, just sketch in. Let's do end behavior here. I know it doesn't say it, but let's talk about it. It would say as x approaches negative infinity, and then we'd also have as x approaches positive infinity. Well, as x approaches negative infinity, as it goes really far left, y would approach 0, right? This asymptote, the x-axis, we could also say, well, that's y equals 0, right? Those are the same thing. As x goes to the right, then y would go to positive. Y would go to positive infinity. All right, let's look at another one. This graph here should say f of x equals negative 2 times 0.5 to the x. Before we even start sketching it, I can say, well, my y-intercept is going to be negative 2. My asymptote is going to be y equals 0, or the x-axis, however you want to think about it. And now we can think about this graph. We know that we have a y-intercept at negative 2, so we're going to have a dot right there. And then we have b would be 0.5, so this is going to be decay. So I know it's going to do something like this. There's going to be one edge, and the other edge is going to be right there. All right, so we can kind of sketch that in, looking something like that. Let's type that in and see if that looks correct. So we'll have negative 2 times 0.5 to the x, and yeah, there we are. That looks pretty similar. I know my graph isn't beautiful, but that's okay. Domain. My domain is going to be all reals. My range, it's going to start down there at negative infinity, less than y, less than, and it gets closer and closer to 0. The end behavior, I'll write that over here. We'd have as x approaches negative infinity and as x approaches positive infinity. As x approaches negative infinity, as it goes to the left, y would be falling, so it would be negative infinity. Y would approach negative infinity. As x goes to the right, y would be approaching 0. Right? Over here on the right, it keeps getting closer and closer to the asymptote there. All right, let's do number 27. This should say f of x equals negative 1 times 1/3 to the x. So really quick, I know that my y-intercept is negative 1. My asymptote is y equals 0. My domain is going to be all reals. My range, I'm going to sketch the graph before I get my range. So if I were to sketch this, I know that my y-intercept is there at negative 1. B is 1/3. Well, that's less than 1, so it's going to be doing a decay. And it'll look something like this. Now I know my range is going to be negative infinity, less than y, less than 0. And I can say my end behavior is as x approaches negative infinity, y approaches negative infinity. As x approaches positive infinity, y would approach 0. I'll go ahead and sketch this on here, or type it in here just so we know for certain that we're correct. So we have negative 1 times 1/3 to the x. Yep, and that looks pretty similar to what we sketched there. All right, I'm going to skip example 28. It's very similar to what we've been doing. Make sure that we have this kind of graph copied down, right? Make sure that we know that if b is more than 1, it's going to be a growth, right? It's going to start off close to the axis, and then it's going to get farther away. If b is bigger than 0 but less than 1, it's going to do a decay. It's going to start off far away from the axis, and then it's going to get really close to the axis. All right, that's all.